Welcome to Liquid Assets. I'm your host, Ravi Kurani. Liquid Assets is a podcast where we talk about the intersection of business, policy, and technology, all as it looks at water. And today we're talking with Tim Bartholomew from NAWI.
Hi, my name is Tim Bartholomew. I'm a research engineer at the National Energy Technology Laboratory, NETL for short, which is in Pittsburgh, Pennsylvania. My research focuses on evaluating the potential of emerging water treatment technologies. A lot of my work is funded by the National Alliance for Water Innovation, NAWI for short, and this is the Department of Energy's desalination hub. I'm a federal employee, but the opinions expressed here are my own and don't represent the U.S. government.
There's a ton of acronyms in today's episode, so we're going to go ahead and jump right into it. Tim, before we jump into your work you do, you had a really interesting point that you made earlier before we hit the record button around your research at Carnegie Mellon and how that tied into kind of what you're doing today at NAWI. Can you just quickly walk us through what you were doing at CMU and what was your research and what were you actually trying to attack?
Yeah, sure. So when I was doing my PhD at Carnegie Mellon, I was evaluating emerging membrane processes for water treatment. So these are new ideas for different technologies. And the specific thing I was doing was called a Techno-Economic assessment, which is when you use models to predict whether a technology can do what it says or even what you think it could be able to do. So the technological performance of it. And then a key part of the Techno-Economic assessment is predicting what the cost would be from it. And so you get rough estimates for what a new technology can cost. You can determine how much it needs to improve and what pathways that make a significant effect and impact on improving that technology. So that's what my PhD focused on at Carnegie Mellon. And then since then, I moved on to the National Energy Technology Laboratory. Both of them are in Pittsburgh. We usually call NETL for short. And I'm doing very similar work under the organization and the funding from the National Alliance for Water Innovation, which was the acronym you said earlier, NAWI.
Got it. Awesome. And just let's zoom up for a second, right, to the 50,000 foot view. There's obviously the National Energy Technology Lab, right? There's this word energy inside there. You guys obviously have the NAWI, which is the National Alliance for Water Innovation. And all of this is held under the DOE, right? The Department of Energy. When you as Tim come into this position, you're looking at this with your team, how do all of these organizations fit together from the research that you're doing, everything you're doing at NAWI, and what are your big picture goals from the organizational standpoint and also from, I don't even know if that stretches up to the DOE side of things, but walk us through what that web looks like.
Sure. It's a very big web. The Department of Energy, it is an agency that funds a lot of research in the country, not just for energy and technologies associated with energy production, but it touches a wide range of things. There's 17 national labs under the Department of Energy, and they do research from all types of things to basically touching all components, except for probably health. So the National Institute of Health has that and medical type of stuff, but a lot of other research falls under the Department of Energy. And so for my line of work, the Department of Energy has created a desalination hub to study water treatment technologies and advance it. And that is the National Alliance for Water Innovation, which is NAWI. NAWI itself is composed of multiple of these national labs, 4 key ones: Lawrence Berkeley National Lab, NETL, NREL, with the National Renewable Energy Laboratory, and Oak Ridge National Laboratory in Tennessee. And there's other national labs that are funded by us in part, but those are the big members. And then dozens of universities and industry partners are all under the NAWI Alliance. And so that's funded to advance technologies, and NETL gets some of that funding to do research at its facility and support its goals. The big picture, why does NAWI exist? And it's really to transform our water treatment that we currently use today. There's a lot of sectors in our economy that use water. Most of our day-to-day life, that falls under municipal. That's how we get our water to our taps and then on the sewer systems in our cities. But a lot of other industries use a lot of water. We have power plants that need it for cooling and for other processes, resource extraction, like oil and gas, mining, all those types of things, just other industries, right? And then agriculture is also a big one. So all of these sectors have a lot of different challenges that vary and are very regionally and other things. But one thing that's common for almost all of them is the overall way they use water, which is what we call a linear water economy. What they do is they extract water from the environment, treat, disinfect, and transport it so that you can use it. And then when you use it, you produce wastewater. You got to treat and transport that to disposal, which is usually discharging to the environment. And so that's a linear process. The idea behind NAWI is to turn this into a circular water economy where you change it from the way you use the water, you produce wastewater, then you reuse the water or you treat it and recycle it again locally. You're not transporting it as much. And then you can produce sellable products from the wastewater that you, like some critical minerals you're able to extract out of it, nitrates and phosphates, or other things like that. And so if we can shift to this, would be a major transformation from a linear water economy to a circular water economy. The benefits are immense. If you can do this circular water economy locally, you could dramatically reduce transport. So you won't have to have these massive transportation systems if you're reusing your water on site. If you can create a valuable product from the wastewater and whatever you extract from it, that can be another source of revenue. But then overall, the impact would be, we would be consuming less water from the environment and releasing less water to the environment. So reducing pollution as well, and have big benefits to society in that way as well. However, we don't currently have the technologies to make this a reality economically, right? Doing this type of treatment is much more expensive than what our linear water economy is now. So we need technological breakthroughs in order to make this a reality. And that's what NAWI is working on. Really early stage, new water treatment technologies that could have an order of magnitude lower cost to make this viable. And it won't be viable for all water sectors, but maybe we can find a way to do that for the power sector in some ways, or some specific industries, and roll it out in that way and reap those benefits as we keep developing technologies.
That's super cool, Tim. So if I just understand, I'm going to unpack a lot of what you just said right now, because I think there's a ton of questions around just what you mentioned. So at the kind of highest level, it's just super interesting that there are these labs. For those of you out there who don't know, the US does have a series of these labs that exist in doing just absolutely amazing, innovative research. And from what I heard you say, NAWI's main goal is to take something that was linear, right? The way that we look at water today is where you're extracting water from the ground, you're using it, and then you have this wastewater that then goes back in the environment. If you're able to basically create something that's circular, you're able to actually just recycle and reuse a ton more, which one helps the supply side of the water problem. But then secondarily, all of that discharge probably goes back in the water. And we've heard stories of groundwater getting contaminated, people not being able to use the initial supply they had before. A lot of those problems end up getting reduced, right? If you have something like this. And it seems like the kind of major linchpin in actually getting this technology to be commercialized is around this wedge of the technology actually being expensive, right? You're not able to actually, today, we don't have the technology available around a treatment side of things to be able to create that circular system. A few questions that I had is, at the 50,000 foot level, like, why can't we just, might be a dumb question, but like, why can't we just create more water? You said desalination earlier, and you guys are part of the desalination hub. Is there a way of just taking our ocean water and like taking out the salts? I've heard that's way too expensive from like an energy standpoint. For the audience, like, can we just create more water?
Right. So we do a lot of seawater desalination. The United States has probably a dozen large commercial plants that do that. They're all located on the coast. It's a solution for the coast. You have access to seawater. You concentrate the brine, so you produce fresh water, but then you have a waste that is even saltier. And in the case of seawaters, we can just put it back out into the ocean. And so that reduces the disposal cost. Inland has a lot harder challenges associated with that. As you're mentioning the costs, I think one great way that I think about the cost is in orders of magnitude, because water has different costs for different sectors. If you take water from a river, treat it, disinfect it, and then like from freshwater source, it costs about 10 cents to do that per meter cube to do that treatment. For seawater desalination, it's about 10 times more expensive. It's $1 per meter cube. And this is not including the transportation and distribution, which varies for every thing. But these is just the treatment cost. But there's other industries like oil and gas industry, which pays $10 per meter cube to treat its really highly concentrated wastewater and to treat that and then reuse it. So the order of magnitude of different costs, it's interesting. Just sometimes I'm talking to people, they think $1 per meter cube, which is our seawater desalination, is cheap compared to the $10 other industry sectors. But yes, right now, like the cost of doing extensive desalination and water treatment is more expensive than if we have a freshwater source. And it always will be. I don't expect technologies to drop it to be the same thing. But if you don't have to transport it anymore, hopefully that brings up the cost to be a similar amount. And then you also get the savings of the energy consumptions. You don't lose any of the water in the distribution systems, which is a big problem. So that's the goal. If you can do it locally, you could pay a lot for your treatment, but you save it on other things.
Which totally makes sense. And so from a water usage systems diagram, right? If you're just looking at who uses water, as you mentioned, there was agriculture, there was power plants, there was the municipal side of things that you guys focus on. If you look at the input side of the equation of the supply of water coming in, we've talked about desal obviously being 10 times more expensive than just taking it from a riparian or like a river system. If you now take a city that uses riparian, right? And we zoom into what you guys are working on at NAWI, once you get that initial supply of water, and you're just saying that if it's in a closed circuit, you can basically not have to continue to keep the tap on, right, from a supply standpoint, and you're able to basically circulate that water that's inside the system. If you guys are then looking at that linchpin, which is the biggest hurdle, which is that technological advancement of making sure that people can do this, what kind of are those technologies, or how much can you speak about in terms of what you're working on and what that kind of linchpin really is?
Yeah. So far in this conversation, we've just been saying technologies, right? Technology.
Yeah.
NAWI is not particular in a specific technology is going to do it. We're not saying that this technology will do it. We're going to advance this technology. Right now, it's broad, and there's broad categories of different types of technologies. Right now, we're looking at membrane processes, like reverse osmosis and modifications of it. We're looking at evaporative technologies. We're looking at electrochemical processes, and it runs the gamut. NAWI is open to anyone's ideas, and most of the ideas that NAWI is exploring are really in the early stages. And so it's a wide variety of different technologies. I will say that in general, right now, the way we do really high salinity desalination is evaporative technologies, and those have been prohibitively expensive and hard to innovate in the last few decades in reducing their costs. So we are looking at membrane processes to maybe replace them in certain aspects. But I think this leads to another thing that like the overall vision of NAWI is like, how do we get different technologies and different categories to actually lower the cost of water treatment and enable this circular water economy? And it goes to another acronym that we developed. It's called APrime. The idea is if you can advance everything in this APrime acronym, then it could make a substantial impact. And the first one is autonomous. If you can reduce the need for human intervention, operators can't be everywhere, especially if we're changing to the circular water economy where you have local treatment and local reuse, you like distributed system. Instead of having large plants, you can't have an operator there running it. And that's very expensive. So if you can get it to run on its own for most of the time, that's a huge thing. If you can make the technology, so that's A. The P is precise. If you can make your treatment be very precise to just treat what is needed. So treat for fit for purpose, right? Maybe you don't have to purify water all the way to reuse it. And that could save a lot of costs if you're very precise in your treatment. And another thing is if you're trying to recover minerals from the water and sell it as a product, if you're very precise in that purification and that type of stuff, there could be some benefits there. So that's the P. R is resilient. So your system can't break down, right? It needs to be reliable. This is a challenge if you're inventing complex technologies that have a lot of parts, right? If it's simple and it's resilient, that's going to go a really long way. It's really hard to quantify that though, especially when you're developing technology. That's the R. The I is intensified. And so the idea is if you change the treatment process from being a series of unit operations to one unit operation that can do all of those things in one go, that can have big benefits because now you don't need all these additional pieces of equipment. So having an intensified unit operation could make a lot of sense. All right, and that's the I. So right now we're at APrime, we're at APRI. The M is modular. And this one is very big. So if your technology is modular and you can manufacture in that way, that means you can do it at a same unit cost at a small scale as a large cost. Right now, our water treatment systems, we make big plants because we reap economies of scale, right? As the thing gets larger and like those types of things, then the unit cost decreases. But the larger we make the plants, the larger the distribution system has to be. So there's a negative effect with the transport costs. If you have a modular technology or a modular manufacturing process, your small scale system costs very similar to the large scale. So that would be huge. And then the last thing is the E, which is electrified. If we can make our water treatment technologies electrified, instead of relying on a lot of chemical inputs, then you have more of a potential for being able to operate those things. If you can get electricity there, that's usually easier than truckloads of chemicals, right? But another big benefit is usually if you bring a lot of chemicals in for chemical treatment, you also create a lot of waste. So you also need to truck out or whatever, dispose of the waste that is from your chemical input as well. And so if you can electrify the process so that you reduce waste and your material inputs, that goes a long way. And one more thing about that is, in general, a lot of industries are considering electrifying because if we make our grid use more renewable energies, it can reduce the greenhouse gas emissions of that process as well. So that's APrime: autonomous, precise, resilient, modular, electrified. If we use those things when we're evaluating technologies of which ones have promise, whichever ones can do those 5 things better are probably having the greatest potential. And some of those are very hard to quantify, but that's how we think we can get there. And we're evaluating a series of different technologies like that. Yeah, I'll pause there.
Yeah, super interesting. And I totally see the kind of through line there around what you did at Carnegie Mellon with the Techno-Economic assessment and like making sure that you have these parameters in which you're actually judging technologies. A few questions here. One around the modular that popped up in my head, right around the APrime side of making a technology that is modular, where you said that we put in so much capital on having these big wastewater plants or whatever plant we're making. And if we can get something that is scalable down to the kind of smallest level, all the way up to its intensified larger scale, do you think there's the opposite problem there for municipalities where the kind of beauty of having a large scale plant is that you do get the economies of scale? And so if you were to take something modular and I think like manufacturing from a standpoint, I can go on Amazon and buy 10 screws that are $1 a piece, but I can go ahead and source it from China or something for pennies. And so is there economies of scale negativity, right, that happens from that modular scale? Or are you also saying in that equation that as you begin to scale up, the technology does have economies of scale when it does get to that larger standard?
Yeah. That's the reason why we have large plants. We get these economies of scale. You can have operators that can control it. And so like the agency has responsibility over it, can make sure that things are safe and roll those things out. The idea with modularity is that the unit costs would be similar. And actually, let me give you a real life example. Right now, reverse osmosis, which is a membrane-based process where you apply really high pressure to push water through a membrane and the salts don't pass through. It is a pretty modular technology, at least the membrane piece of equipment. They spiral around modules. And if you want a bigger plant, you just buy more of them and put them in parallel and series. We still make large scale plants of that because we get benefits on the intake, the pumps, and other things like that. But a technology that isn't modular, that does the same thing as reverse osmosis, would be like an evaporative process, like mechanical vapor compression or multi-effect distillation. These are big reactors that evaporate the water, and they're giant metal tanks, essentially. And if you wanted to add a little bit more capacity, you can't just add a smaller metal tank. You'd have to like this thing. So those have locked in like big pieces of equipment. Whereas the RO, if you want to go from a larger plant, you just add some more of these modular things. If we can innovate the RO process so the other components are modular in nature as well, hopefully that small system can cost similar as the large scale system, and then you can reduce the distribution cost. But that is a big challenge. I think the counter to it is it's very unlikely if we keep with large centralized treatment facilities that we can get to the circular water economy, because to take all the wastewater and mix it all together, you can't do precise, like pulling out the resources you want, or do fit for purpose treatment for the specific use. And so I think the only way to get to the circular water economy is to make it be distributed in a lot of ways. And maybe that means municipal water sector is not our main target. It might be more of the industry specific ones, or maybe potentially, I know there's equivalents of electric grids, having a microgrid for electricity. I think this was actually mentioned in a previous podcast with another person. Well, an idea is to do this for water, do a micro grid for water. And maybe a whole community has that, right? So yeah, I think, did I answer your question?
Yep.
Hopefully modular manufacturing keeps the costs the same, and you can do distributed, then cut out transportation costs. Then the circular water economy realize it. It'd be very difficult doing a central treatment for this type of idea. It's transformed.
Got it. And I think from your APrime acronym, I think the precise and intensified makes way more sense now, where if you're focusing on a particular industry or a particular market that like could use that technology, it makes a ton more sense than having a one-to-many equation of a wastewater plant, and then making something that's a little bit more decentralized, comes down from a spectrum standpoint where you're not having a one-to-many given a large city or potentially something like that, but more on-site, on-premise, which I think goes back to your autonomous standpoint as well. Totally makes sense.
Yeah. And I guess, so this kind of leads to, I think you mentioned my techno-economic assessment work at Carnegie Mellon. That's still the same type of work I'm doing for NAWI. So if we think of the R&D life cycle for technology, like how do we go through this? And first there's a concept, right? You have some sort of idea that maybe this will do it. And you like can test that concept either at the bench scale or through some initial modeling to see if that would work. And then you create a device at the bench, pilot, and eventually commercial scale. And then throughout this whole process, you're refining and optimizing the technology. And so my team's role, we help by providing modeling along the way, specifically doing techno-economic assessments, which means if there's this idea, what are the fundamental phenomenon that this technology is going to do? Can we model it to predict how it will perform and see how that goes? Compare that to current technologies, right? And specifically, we look at the levelized cost of water, which is very similar to the levelized cost of energy, the dollars per kilowatt hour or cents per kilowatt hour that we frequently talk about in energy. There could be a dollars per meter cubed of product water for water. And this includes the capital and operating costs. And so with doing this modeling alongside these early concepts, we can find out which ones have the most promise and potential. And that's what our main goal is. My team, we're working on a technology or a software product called WaterTap, which enables researchers to do techno-economic assessments easier. And that's what we're really pushing for. An example of this is there's a lot of different ways. Reverse osmosis is our primary desalination technology that we and the US and the world uses. But there's modifications you can make for reverse osmosis that allow it to operate in ways that it's not currently being used, like going up to higher salinities and concentrated brines, things like that. And so all of these modifications to reverse osmosis have a lot of different names. I'm just going to include a few. You can do high pressure reverse osmosis. You can do osmotically assisted reverse osmosis, low salt reduction reverse osmosis. These are all just different ways to configure reverse osmosis and operate it in different ways. And we have analyzed those different technologies and projected what their levelized costs would be if they're deployed at commercial scale. And one thing about predicting costs, it's hard to nail down an exact number because costs can change from vendor to vendor. It can change for new technologies that haven't been developed. So what we oftentimes do is do sensitivity analyses. We take a parameter, we assume like the membrane cost $50 per meter squared. We range it from 30 to 100 and see what impact that has on that levelized cost of water. And then we can also identify targets. Hey, it has to be at this level in order to be economically viable in this situation, right? And that's the type of analyses we've done. A lot of them have been around these modified reverse osmosis products, which show a lot of promise.
Okay, super cool.
Show a lot of promise. Yeah.
And so just so I understand the way that WaterTap, the software, is accessible, is this the first question that I have around the technologies that you guys are looking at? Is the majority of your supply of technologies coming through the national labs, or do you also use startups or other technologies that are out there and put them all together? Or is most of your assessments from the national labs?
So we create models on technologies that are prioritized by our funders. The National Alliance of Water Innovation has identified a series of technologies that show promise. And so we develop technologies for that. We have some other funding from the Solar Energy Technology Office that's looking at solar-driven desalination technologies. Other funding from the Industrial Efficiency and Decarbonization Office. They're all under DOE, the Department of Energy, but they're really looking at like biological wastewater treatment. So we've created models for them. Another thing that we create models for and how we prioritize them is we also create models for the standard desalination technologies that are currently there so that we can compare the new technologies against them. So that's how we get our priorities, is based on what our funding sources are looking into. So no, we don't take specific examples out in startups or things like that and see how it would perform. However, most of our research organization is on not a specific device, but like a type of technology. Right. There's a whole bunch of ways to do reverse osmosis. And we develop an electrodialysis model, let's say, which could be applicable to a whole bunch of different companies that are looking at different ways and different devices. And we're still modeling the fundamental driving force that can do some predictions on it, even though it's not to the very minor details that make the devices different from each other.
Got it. Okay, that makes a ton of sense. And so then if we take this electrodialysis example, do you then, from the WaterTap assessment, push this out to the folks in the labs to say, hey, look, this is the target that we developed for the electrodialysis technology umbrella. These are the targets you need to hit. And so then go for it, make something up. Or what happens after that, after this was actually made?
Yeah, so our analyses inform our research programs. Besides setting research targets, that I mentioned before, we can also determine bottlenecks. Hey, this is a core feature of this technology and this constraint you can't get away from, and you're going to have a minimum cost of this or something like that. So bottlenecks, we can identify those things. And then we can also incorporate the technologies in with other technologies because we can analyze treatment trains and see what impact or benefits there are of using multiple technologies. But who gets informed of our stuff? We make internal reports to our research programs and say, hey, this technology is seeing more promise. The main way, though, oftentimes our funding organizations, they're funding current projects that are doing experimental work on new technologies. And we partner up with those projects and do the techno-economic assessment alongside of them. So then they can help prioritize what things they're going to focus on improving their technology, right? There's all these decisions you can make on optimizing your technology. And we're hopeful that our types of predictions and trying to project that out to the eventual cost will help guide it to, these are the main things we need to focus on, get this thing through the door. So we help the individual projects under our funding organizations. And then we also create publications for our work that people can access in the general water research community. So
got it. Cool.
Those are the impact.
And WaterTap is generally, it's a pretty new product, right? So what is as much as you can share, what does the roadmap look like? What does the future of WaterTap look like?
Sure. So WaterTap is an open source software and it's on GitHub and anybody can download it today and use it. The key thing about WaterTap is it is a research tool, right? So it's designed for researchers to analyze their new technology, which means it needs to be very customizable and flexible, right? We don't have like support. Oh, you have this exact technology. We have a model for that, right? We more have a variety of different models that can be modified to represent your technology. And then you can do an analysis and that takes time to know how to use it. And a key barrier, I think, for most people is our software tool, you use it through coding. It's a coding interface. If your viewers are familiar with Python, there's Python packages you can use to do certain things like pandas to visualize and modify and use your data and other things like that. WaterTap is a Python package. You install it and then you can create models for water treatment processes, hook them up into a treatment train and do techno-economic assessments. A lot of our special sauce is how we do the techno-economic assessment. We support really advanced optimization capability. It's called equation-oriented modeling, but that allows us to solve these complex problems and do cost optimization when we're analyzing the process. Anyone can use it. It's just, there's a lot of skills you need to have in order to use it because our users, the people we're really targeting are other researchers like us, like these individual project teams that have a year to analyze and improve their technology. And then our secondary users, as WaterTap becomes more mature, has been used in a variety of different analyses, is to make this available for engineering consulting firms to do analyses and explore technologies in that way. But usually, once you get into that frame of mind, you have to have a quick turnaround for those analyses and a lot of capability there. Generally, our users would build a model over a series of months and analyze it, and it takes time. So it's definitely a research tool, but it's accessible now to the public.
Awesome. Really cool. And if they wanted to, they could just search on Google WaterTap GitHub and like it should pop up, or what's the way to access it?
I haven't actually done that very much. Maybe my Google is tainted because it knows who I am, but let me just put in a WaterTap, get and see what the first link will be. Yep. It is the first link for me, at least. And that is our GitHub site, and we have documentation off to the side of it. Yep.
Cool. Really cool. I want to take a quick left turn a little bit, Tim, because our audience is a pretty wide spectrum, and the folks that we have on the podcast are just one, inspirational, but secondarily, they come from all walks of life. And so the fact that you did this PhD at Carnegie Mellon, you're working with WaterTap and NAWI, why did you decide to do the PhD, right? Like, what was the life of Tim before that? What kind of guided you into wanting to solve these water problems and building this techno-economic assessment?
Yeah. So I always think life is all about serendipitous opportunities that just come and you just like, oh, this I think is the best path. I'm going to choose it. And so for me, I was doing a chemical engineering degree at Washington University in St. Louis. And a lot of my summer internships were research-based. I went to different universities and did 10-week research. So a lot of my experience and resume was building up to continue to do research. But one key thing I learned during my research is I didn't like just looking at, I did a lot of computational chemistry for my internships, which looked at how atoms interacted with each other. You arrange them in different ways and calculate their energy, and maybe this low energy state is the state it's in most frequently. And I liked the different impacts of it. It was for solar energy production and catalysis for biofuel production. But I wanted to do more system-wide thinking. And so when I was applying to grad school, I got an opportunity at Carnegie Mellon to do process systems engineering, which is looking at things at the process scale, so at the equipment level, and using optimization to do that. And that's what really attracted me. I went for this optimization, analyzing technologies at the process scale, and water treatment just happened to be the application of that project that I received funding for. So it was just an opportunity that happened, and I got into the water treatment space, and then I became an expert in water treatment, and I'm still applying those same skills today. I think it's really important. Water is a major challenge for the country and for the world, but it just happened that way. Instead of me necessarily choosing water, it was an opportunity I was given, and I've stayed with it.
Awesome. Yeah. And I think your point on serendipity comes up a lot, right? I think people fall into a lot of what they are. And you look at hindsight 2020, and there really isn't a clear path. If you were where you were 20 years ago or 10 years ago, you're not like, hey, Tim in the future would have planned this path. It's where you arrived at, which is just really cool. I asked everybody on the podcast this question, and it's, do you have a book, a TV show, or a movie that has potentially either changed your outlook on the way that you look at water, or just the way that you look at life, right? Something that's changed in you when you watched this.
Yeah, it's not related to water, but Range by David Epstein.
Okay.
It is the big small, which is Range, How Generalists Triumph in a Specialized World. And I read this book, and it totally changed my outlook on career trajectory and career paths. It really pushes against the 10,000 hour. Like, in order to become an expert in something, you need focused training of 10,000 hours, right?
Yes.
It actually states the opposite, that most people that have gone really far in their careers, they've taken a winding path and have picked up a broad range of skills and knowledge and been able to connect those things to make a new product or a new thing. And so it flips it from, if you ever think you're behind in a certain field or something, it flips it from, I need to spend 5 years, 10 years to do something like this, or to what can I use the skills that I've picked up with all of my experiences along the way to advance this thing or continue my career. And it makes every experience not like a wasted experience. You learn something. And so it really changed my whole mind on career paths. Yeah.
That's awesome. I love that. Range by David Epstein. We're going to go ahead and throw those into the show notes when we publish the episode as well. Tim, thank you so much for coming on this episode of Liquid Assets. This has been super insightful for us to understand the world of DOE and NAWI and NETL. Thanks again.
Thank you for having me.
And for all of those of you out there, if you want to listen to Liquid Assets, you can find us at liquidassets.cc or anywhere else you get your podcasts or on YouTube today.